Hey guys, welcome to our third set of notes for chapter 15. I apologize for the late post, and this is going to be kind of a short set because, for better or worse, you're kind of catching up to me a little bit. So I'm only working a couple days ahead of you. So I'll get you to where I am, and then you'll be able to catch up to me, and we'll just work from there. So this will be a brief one. This is where we left off last time. It was weak bases and base ionization constants. This is going to be very similar to Ka. The difference you'll note right away is with acids we were working with like Ha yields H plus plus A minus. There's really no water involved because as long as we could give up that hydrogen, we were pretty much happy. With weak bases, we're going to add water into this because the bases have to accept a hydrogen and they can't just kind of pull them out of thin air. So most of your bases are going to be dissolved in water, and so we're going to do your base plus water yields, the conjugate acid. So you add an extra hydrogen in that plus, and then the OH minus ions, and that's going to be really valuable. From there, you can calculate pOH. From pOH, you subtract it from 14, you can get to pH, all sorts of stuff. So we're going to include water in this, but because it's a solvent and its Kw is super, super small, we actually kind of cancel him out when we do ice problems. We just focus on our base and our conjugate acid and our hydroxide ions. So know that while we're writing water in, he's not written in the equilibrium expression because it's a solvent. And so we don't consider him very much. We really don't consider him at all in our calculations. So there's the big difference. Kb is the base ionization constant, and it's very similar to Ka. So of course, if we increase Kb, that means we're producing a lot more products than reactants. And one of those products is the OH minus ion, which is a measure of how strong our base is. So if Kb is very large, then we have, this is weird to say, a stronger weak base. As far as weak bases are concerned, it's stronger if it has a bigger Kb because it's ionizing into more OH minus ions. So we solve weak base problems exactly like we solve weak acid problems, except for we don't solve for hydrogen ions anymore. We solve for OH minus ions. And then we can solve for pOH and pH and all sorts of stuff from there, really. But you're still going to use ice, and you're still going to solve for X using quadratics, all that stuff. It's exactly the same. We just add water, and we focus on hydroxide ions. So we'll practice those a lot. Here's a table of some weak bases and their conjugate acids. It's in your book. You can look up the weak base. If in the problem they don't give you the Kb, you can find it here. There's caffeine. Nice. And you can find its Kb value and use that as the constant. So, ionization constants of conjugate acid-base pairs. Here's our acid. We use a Ka for that. Here's our base. We use a Kb. Might not be a bad idea to write these down. These are really nice general formulas to compare how you solve an acid equilibrium problem, how you solve a base equilibrium problem, and they are both very important. So if we put them together, really what we end up with is water ionizing, which is kind of cool because this is Kw. It's something we actually talked about at the very beginning of acids and bases. And so a Ka and a Kb are related to Kw. And if you recall from using Hess's law and adding these things up earlier, I'm not sure, it might have been chapter 13 where we did this and we said we had to multiply them. That's exactly what we're doing here. We're applying this concept to this, which is K sub A multiplied by K sub B equals K sub W, or the water ionization constant, 1 times 10 to the negative 14. And so you could solve for a weak acid and its conjugate base. You know Kw. If you know Kb, you could solve for Ka. It's kind of cool. And they both have to add to 1 times 10 to the negative 14. And then you can do the same thing, rearrange the formula to solve for Kb. Whatever you need to solve for, you can. So those are very important. Easy equation to use. So here's a little trickier concept. These are diprotic and triprotic acids. Up until this point, we've worked with monoprotic acids, which means one proton. And those acids, it's the Ha yields A minus plus H plus. We only have one hydrogen to give away, so it makes it a little simpler. Not all acids are like that. Quite a few acids will yield more than one hydrogen ion per molecule, but they don't just immediately throw out 2 or 3 hydrogens all at once. They actually ionize in a stepwise manner. So they lose one hydrogen,
and then they lose another hydrogen later. And then if they have another one, they lose that last one later. So an ionization constant expression, we actually have to write it for each ionization stage. So we have to write the breakdown in 2 different steps or 3 different steps. You got to do it for each time it loses a hydrogen. So consequently, 2 or more equilibrium constant expressions must often be used to calculate the concentrations of the species in the acid solution. That's a wordy way to saying, as much as you're going to hate this news, you get to use ice twice in one problem, and then add the products of your hydrogen ions concentrations to figure out the overall pH of your solution. So not fun by any means, but doable, assuming you don't run out of space on a piece of paper. And so here we can say we've got H2CO3 ionizes to release hydrogen, and HCO3 minus, which is, its conjugate base, but that conjugate base is actually still a weak acid. And so we can take this guy into the next problem and say HCO3 minus ionizes to give off a hydrogen ion and just a carbonate ion, and write another Ka equilibrium expression. You can see that we have 2 separate hydrogen concentrations, and they'll very likely be different. And we have 2 equilibrium expressions, and those will also be different. So diprotic and triprotic acids just make this one step more to do from a math point of view, but solving the problem is actually very similar. And so here is a table from your book, and it's some diprotic and polyprotic acids. So H2SO4 has 2 hydrogens to give off. Its Ka is very large. That's a hint that you can assume it pretty much completely dissociates. But here,
Luca, are you in the building?
Here we have hydrogen sulfate ion, and it is a much weaker acid because it's given up one of those hydrogens, and it doesn't really want to give up that other one quite as much, so it has kind of a small Ka. So here's just some comparisons of different diprotic acids. So the last thing we're going to talk about for this set of notes is how strong is your acid? Can we look at what makes up the acid and find a trend for whether it's a strong acid or a weak acid? And the answer is yeah, we kind of can. Here we're saying that H is bonded to X. It could be anything, fluorine, chlorine, some long organic molecule, whatever. But it ionizes to give up the H plus and that X minus ion. So if we have a really strong bond here, is X going to readily give up that hydrogen, or is he going to kind of hold on to him? Well, he's going to kind of hold on to him. It's a really strong bond. So if we have a really strong bond here, it's going to be a weak acid. We are not going to want to completely dissociate it into ions because we're holding on tightly to that hydrogen bond. And so here we can look at this, and we can kind of look at electronegativity. If you remember from periodic trends, electronegativity decreases as you progress down a group on the periodic table. And it's no different here. A hydrofluoric acid is a very, very weak acid. Why? Because he's holding onto that hydrogen very tightly. Hydrochloric acid is a little bit stronger acid because he's not holding on as tightly. Hydrobromic is a strong acid because he's not holding on as tightly. And hydroiodic acid is a strong acid because he's not holding on very tightly. And so the strength of our bond has a lot to do with how strong our acid is. And here you can see your periodic table. Acidity is increasing as electronegativity is decreasing. So here they're just showing some bond enthalpy numbers. Weak, strong, strong, strong. And you can see that the bond enthalpy is decreasing. So how much energy does it take to break this bond? That's bond enthalpy. It takes a lot of energy to break hydrogen fluoride. That's why it's a weak acid. It doesn't take that much to break hydrogen and iodine. That's why it's a strong acid. It gives up that hydrogen pretty readily. So this is the last thing we're going to talk about. It's an oxoacid strength. So we have oxygen in this acid, and that's going to change things up just a little bit. You can see that we have oxygen attracted to hydrogen because oxygen is partially negative, hydrogen's partially positive. This is going to be a little bit polar as a molecule. Who knows what this could be back here, but this end is most certainly polar. Oxygen will let go of hydrogen, but not super readily. The OH bond will be more polar, and it's easier to break if Z is very electronegative. Now, hopefully that makes conceptual sense. We got electrons being shared between oxygen and hydrogen. We have electrons being shared between oxygen and Z, whatever atom or molecule is on the other end of that. And if oxygen is going to let go of hydrogen, we need to weaken this bond right here. And if Z is really, really greedy, then he's going to pull more electrons to this side, which is going to pull more electrons to this side. And they're not going to be so evenly shared here, and it will be a little easier to break that bond. If Z is in a very high oxidation state, that will also make this bond a little bit easier to break. And so here's an example of a whole bunch of oxo acids where as we change what's connected to the OH, we change the strength of the acid. And so there's just a few different examples of those. Alrighty, so oxo acids, if they have different central atoms that are from the same group and have the same oxidation number, our acid strength will increase if we increase that electronegativity of Z. And so that's not a big surprise because it's kind of what we just talked about here. If you look at your periodic table, chlorine's a lot more electronegative than bromine. So this will be the stronger acid. And there you have it. So acidity increases in oxo acids as we increase electronegativity. Alright, so what if they have different numbers of attached groups? Acid strengths are going to increase as the oxidation number of Z increases. And so here we haven't done oxidation numbers in a long time. If you remember Leo goes Gur, chlorine normally has 7 valence. Here we have 1, 2, 3, 4, 5, 6. So she's a +1 right here. Chlorine normally has 7 valence. We have 1, 2, 3, 4 here, so it's a +3. Normally has 7. We have 2 here, so we're +5. Normally have 7. We have no valence here, so we're +7. And so as the oxidation number of this increases, we're actually going to have a stronger acid. So weakest acid, stronger acid, stronger acid, strongest acid, because it has the highest oxidation number. So there's that trend. All right, so salts is actually where we're going to end for this time. Hopefully I gave you enough information to give you a little confidence moving ahead into the next set of questions. So that's where we'll end for today. Thank you.